Good day, everybody, and welcome to this first lecture on our second term, which is the medicinal chemistry section of the Drug Design and Medicinal Chemistry PCH 312 course. So when you go through the medicinal chemistry section, you will note that on the Canva platform, there is a tab as indicated as medicinal chemistry. You will find some introductory notes to medicinal chemistry, as well as the different lessons that we'll be looking at during the course of this term. You will also note next to each lecture or lesson, you will find the dates when each lesson needs to be done. For this week, which is the week of 11th to 15th of April, we will be looking at the introduction to medicinal chemistry, the general anesthetics, as well as the local anesthetics. So let's get right into it. So just to give you some background on medicinal chemistry now, how I see medicinal chemistry, it is basically where drug design and discovery and pharmacology merges. So you will see with medicinal chemistry, a lot of the aspects of drug design and discovery is still contained, but we are now specifically looking at different drug classes. So these drugs have already been discovered. They've gone through clinical trials, and now we're looking at medicinal chemistry. It's pharmacology, as well as the chemistry associated with the pharmacology of these different drug classes. And as I've indicated here, medicinal chemistry is a stimulating field that links many scientific disciplines and allows for collaboration with other scientists in researching and developing new drugs. So very similar to drug design and discovery, you can't do medicinal chemistry in isolation. You always work in a multidisciplinary or an interdisciplinary field, or interdisciplinary collaboration to be able to do research in medicinal chemistry. This is then just like a brief overview again of the drug design and discovery process. We've already discussed high throughput assays, how you do lead compound identification, how you develop structure-activity relationships, and then even where we do structural characterization of protein ligand complexes. Think about the docking, where we could see how our compound was able to then bind to the active site of a target protein. So it's always important to keep in mind the drug discovery process. Even though we are doing medicinal chemistry now, we always need to know where these drugs and these different drug classes came from this drug discovery process. Now, in the medicinal chemistry course for this second term, we will be focusing mainly on our central nervous system acting drugs like our general anesthetics, the sedative hypnotics, antipsychotics, and our anti-Parkinsonian drugs, to name a few. We will also do a short section on the cardiovascular drugs, especially the ACE inhibitors, which are used as antihypertensives. And we will look at both the pharmacology as well as the chemistry of all of these drug classes. And I will show you what you can learn from the chemistry that will enable you to understand the pharmacology better as well. Now, this medicinal chemistry course won't stop at the end of this term. You will see next semester, we will continue with medicinal chemistry. We will further build on our knowledge, further build on the knowledge that we've gained from our drug design and discovery. And Mrs. Cup will then take you through other drug classes where we combine the drug design and pharmacology to give us then the medicinal chemistry course in your third year, second semester. For this section, we will be looking at the general anesthetics. So the general anesthetics, there is a textbook that you will need, but I've already loaded the chapter of this textbook on eCanva. I do have the permission to share this textbook with you because it is less than 10% of the textbook that we are sharing, and we are allowed to do that. So you'll see this chapter is 4S Principles of Medicinal Chemistry, the 7th edition, and the section on general anesthetics is from page 508 to 522. Now, it is important for you to go through these different sections within the textbook. But it's also important to note the following, that the majority of the exam questions, about 95% of my questions from this section will come from my slides, my notes, and my study questions. The questions posted on the lesson platform will be used to develop the majority of the exam questions, and you will note that my study questions, if you can answer about 80% of those study questions without referring to the material, then you've reached the objectives of this section. So let's talk a little bit about what anesthesia is and the definition of it. So the most basic definition is basically where you have a loss of sensation of pain without the loss of consciousness. You can have a look at the definition and further information on anesthesia in our textbook chapter on page 509 as part of your introduction. It is also very important for you to have a look at the video clip. There's an introductory video clip that takes you through what anesthesia is, what general anesthetics are, also local anesthetics. It takes you through the pharmacological mechanism of action of these drugs, and also talks about action potentials and further pharmacological mechanisms. So please make sure that you do go through the video clip as well, and also just read through the introduction on general anesthetics to get a good idea of what this section is about. It would also be to your benefit maybe to write down your own definition of both general anesthetics and what anesthesia means, because that could be a nice short question to ask in the exams. Just some further background. So before we discovered these drugs that we can use as general anesthetics or as general anesthetics, before that we did not have any medicine that we could use during surgical and dental procedures. And what they used in the mid-1980s and even before that, they would use physical methods like a blow to the head, packing limb with ice, and holding the patient down during these surgical and dental procedures. Then a little bit later on, researchers did find that if you use certain chemical methods, you could then induce anesthesia. And some of the chemical methods used was the opium poppy. So the opium plant contains morphine, and they found that if they had high concentrations of this opium intoxication, then it leads to a general anesthetic effect. Also, like alcohol, ethanol, it's been used throughout history where large amounts of alcohol is consumed. You can lose consciousness, and it also reduces your perception of pain. But obviously, we know of all of the adverse and the bad effects of ethanol and alcohol. So that is not something that we are using in modern day medicine. So luckily, we are in 2022, and there are much better medicines now compared to these old methods that we used to induce general anesthesia. It's also important maybe to go and read up on the history of this on page 508. Then just to show you the different drug classes. So all of these different drug classes do have some anesthetic properties. Not all of them are used as general anesthetics, but these drugs are the ones that do have some general anesthetic effects. And they include some of the central nervous system depressants, like your general analgesics, certain sedative hypnotics, like your benzodiazepines and your barbiturates. Certain anticonvulsants as well have some anesthetic effect. But the main thing that I want you to know from this slide is that the general anesthetics have varied mechanisms of action. They are non-specific drugs. They can work on various different targets at the same time. But all of these targets then basically leads to an interference with sensory and motor conductance. So that's basically where it then cuts off your perception of pain. We'll look at the mechanism of action a little bit more in depth later on in the slides, but also in your introductory video clip, the mechanism of action of the general anesthetics is very well explained there. So my suggestion would be for the mechanism of action, go through the video clip again and write down the mechanism of action, this varied mechanism of action of the general anesthetics. Then you will also see the generation of action potential and the way in which we then feel pain or get our pain perception, and also how this action potential can then be stopped. So this is also quite important. You can read up on the mechanism of action on page 525 in 4 years, but also the video clip. It does give you some background information on what the action potential is. I would like you to summarize this in your own words into 4 or 5 sentences on the mechanism of action and where you can see then an action potential. This is mainly for background, and there may be 1 or 2 MCQ questions in the exam, because this is more pharmacology and physiology. But if you want to understand general anesthetics and local anesthetics for that matter, you have to have a sound knowledge of what the action potential is and then the mechanism of action of the general anesthetic. So please do put in some time and write it down for yourself in just 4 or 5 sentences to get a good understanding of what an action potential is. Then, furthermore, we get 2 different types of anesthetics, our general anesthetics and our local anesthetics. So general anesthetics is basically where you lose consciousness. It's used during surgical procedures, and it's where you produce a partial or complete loss of the sense of pain. In the case of general anesthetics, this is accompanied with by a loss of consciousness. So if we read through that again, anesthetics are the present drugs that produce a partial or total loss of the sense of pain. In the case of general anesthetics, this is accompanied by a loss of consciousness. So what I want you to do here is to think about what are the main differences between, that you already know, the main differences between general versus local anesthetics. How many of these differences can you come up with? We will discuss this in the next lesson as well, where I have a slide which indicates the main differences, but please do not go to that slide yet. See how you can use your knowledge that you've gained throughout the years in pharmacology and where you've discussed general and local anesthetics, and how many of these differences can you come up with without referring to my slide in the next lesson. I think this is quite a nice exercise just to see how much you already know before moving to the medicinal chemistry of general and local anesthetics. Now, the different drug classes, and specifically we're going to look at general anesthetics now. So the different drug classes in this group are inhaled general anesthetics. Now, the inhaled general anesthetics are on 2 subclasses, are hydrocarbons that do not contain a halogen. Halogens are like fluorine, chlorine, and bromine. And then we have our improved agents, the halogenated hydrocarbons that do contain either bromine, chlorine, or a fluorine within its structure. There's also a 3rd class of the inhaled general anesthetics, and that's just nitric oxide. That is not a very potent general anesthetic, but it is still routinely used during dental procedures. Then we have our intravenous general anesthetics that we will briefly have a look at, and also other general anesthetics like our alcohols. As we've previously said, ethanol has been used throughout history as a general anesthetic. And because of that reason, some researchers have looked at improving on the structure of ethanol to reduce toxicity and to improve the general anesthetic effect. So we'll look at some other alcohols other than ethanol and look at their structures and structure-activity relationships as well. It is important to have a look at the intro video clip for an excellent explanation of the different general anesthetic drugs as well as the mechanism of action. So please make sure to put in some effort to go through that video clip and take notes. Then for general anesthesia, it occurs in 4 distinct stages. I'm not going to go through this now. You do have my notes, and you have in the textbook on pages 510 to 511 the stages of anesthesia, and a very nice explanation as well in the introductory video. Make sure that you understand it. Make sure that you understand that stage 1 is analgesia. It moves then over to delirium. Then it's surgical anesthesia. And once you get to stage 4, that's respiratory paralysis or also overdose that can lead to cardiac arrest or respiratory paralysis. So please make sure that you do go through this, that you put in the effort. And yeah, could be a nice exam question, either as an MCQ or as a longer descriptive type question. You'll see in the textbook on page 511, it also then takes you through a schematic showing you the different stages and what happens when you are awake, when surgery commences, and so forth, and also the different effects of each of these different stages of anesthesia. Now, obviously, you never want to get to stage 4 because once it gets into stage 4 in anesthesia, then you are in problems, because that is an overdose, and they will, and the doctors will have to then intervene. This is then just an example. If we do ask you to discuss the stages of anesthesia and how you can go about it to give your answer, and where we then look into giving the different marks as well. So I hope that this gives you some feedback on what we are expecting in the exams and ways in which you then answer the question, and also to give you an idea of for which different facts we do give a mark. Each of these marks count half a mark per fact. So please make sure that you go through this so that you get an idea of how we mark your answers in the exams. Then some general considerations for the general anesthetics. So most general anesthetics are non-specific drugs, like we've already said. So for non-specific drugs, like we said in the drug design and discovery section, non-specific drugs, you can't really get much structure-activity relationships from it, because it does not just work on a single target. Like, for instance, the general anesthetics can work on chloride channels, the NMDA receptor channel, the cholinergic receptors. I mean, there's quite a few different targets that it can interact with to give the general anesthetic effect. So because you don't have a single target, it is extremely difficult to develop structure-activity relationships for these non-specific agents. And their activity is mainly dependent on the lipid solubility. So the more lipid soluble the drug is, the more of it will actually then reach the brain. So if we then also look at the inhaled general anesthetics, so the volatile general anesthetics, that is an inhalation agent. So you put that mask on, you inhale that gas, and it gives you the anesthetic effect. So the way that this works is you get the inhaled gas, it goes into your lungs, it then equilibrates with the lung tissue, the alveoli. It then gets absorbed through your lungs, it gets into your bloodstream, and then it reaches your brain, the central nervous system. The more lipophilic this drug is, the more of it will reach the brain. The more of it will dissolve in the alveoli, more of it will be taken up in the blood, and more of it will then reach the brain as the lipid solubility increases. And then the mechanism of action, like I've already discussed, is that with these diverse structures, the SARs are still not fully understood, even after 150 years of research, even more now, probably closer to 160 years of research now. But it is known that ion channels like chloride channels and certain brain receptors like GABA, serotonin, the acetylcholine receptors, and the NMDA receptor plays a role in anesthesia. You can go and have a look at the complete background on the mechanism of action for general anesthetics from page 513 to 516. And this is for self-study, and there may be 2 or 3 exam questions that may come from this section. What I would like you guys to take note of here is this simplified mechanism of action, where the gas gets inhaled, goes to the alveoli, goes in the blood, goes into the brain. The more lipophilic the drug, more of it will reach the brain. Then there's also some characteristics of an ideal local anesthetic. I'm not going to go through each of them. You can go and have a look at on page 524 of the textbook as well. But you can see all of these different characteristics, but unfortunately, even up until today, there's no ideal general anesthetic that has been discovered. So there's still research going on to improve on the properties of general anesthetics. So even further improving its margin of safety, making it non-toxic, reducing the flammability and the explosiveness of these general anesthetics, because some of these volatile or inhalation general anesthetics are flammable and quite explosive. They get actually stored in these large gas cylinders. And if you do get it into contact with fire also, then it can be flammable. So we are still trying to improve on the properties of general anesthetics. So there's still an unmet medical need, mainly because of certain toxic effects of the general anesthetics, as well as some of its chemical properties, like, for instance, it being flammable and explosive, which could be quite hazardous in a hospital setting. So it is still continuing to improve on the properties of general anesthetics, and research is ongoing. Now let's look at each of the different drug classes for the general anesthetics. The first one that we will be looking at is our inhaled general anesthetics. And the first one is the non-halogenated hydrocarbons, like for instance, cyclopropane. Non-halogenated, meaning it does not have a fluorine, bromine, or a chlorine moiety connected to the hydrocarbons. So let's have a look at some of these non-halogenated hydrocarbons. You can also read on it further on page 516 of FOIAs. So many short alkanes, alkenes, alkene having the double bond, alkyne having the triple bond, are capable of producing anesthesia. So all three of these different small molecules does have some general anesthetic effect. And some of the structure-activity relationships that they could come up with, it's a very few, and it's because of these compounds are non-selective. They did find that an increase in carbon chain length from a 1 carbon to an 8 carbon does increase the potency of these type of drugs. But unfortunately, as the potency increases, so does the toxicity as well. So you will move from a 1 carbon to an 8 carbon, but then you have a drug that's more potent in the 8 carbon, but you see all of the toxic effects, like for instance, severe cardiovascular toxicity. And as the carbon chain length increases as well, it becomes highly flammable. And because of these reasons, these agents are not useful general anesthetics. But these compounds were quite nice lead compounds. And researchers use these lead compounds then to come up with a drug that is currently on the market and still used today. It's cyclopropane. And cyclopropane, you can see, is just a hydrocarbon, but it's a cyclic hydrocarbon. So they've done a type of a ring chain transformation, like we've learned in our drug design. And this hydrocarbon is still being used today. So you can see how this then already started out as lead compounds to give us cyclopropane. Then this is just, again, an example of an exam question. If we ask you to write short notes on non-halogenated hydrocarbons, you can see there how we would like you to provide that, and also giving you some tips on what you need to focus on if such a question is asked in the exam. Now, from the non-halogenated hydrocarbons, from those lead compounds that the researchers identified, then they moved over to halogenated hydrocarbons, because they found that if you include a bromine, chlorine, or a fluorine into the structure of these type of alkanes, sorry, let me just get to it. So for instance, with these alkenes and alkanes, they found that if you now include the halogens, so for instance, a fluorine maybe on this position or a chlorine on this position, then you do improve the properties of the hydrocarbons. So let's have a look at some of the initial halogenated hydrocarbons that were discovered from our non-halogenated hydrocarbons. So the first two that were discovered is ether and chloroform. Now, these agents were also then at that time known as anesthetics from hell, because they have all of the negative traits of this drug class. So they are definitely not ideal general anesthetics. So if we look at the ethers, here you have the ethers, just 3 examples of ethers. So the ether is where you have like a oxygen that is connected to 2 carbons. That's an ether bond. And you can see the ethers do resemble that of the non-halogenated hydrocarbons. And you can see here diethyl ether. It is it contains its alkyne group, but it's connected to the ether. Then we have the divinyl ether. Here we can see that they've included some double bonds. And then they got to a drug that is a little bit better. It's fluoroxine, and fluoroxine contains the fluorine, which is a halogen. But like I said, ether and chloroform are anesthetics from hell. If we look at the ethers, ethers with a low molecular weight have potent anesthetic activity, which is good. But unfortunately, they do have some negative traits, like for instance, they are flammable, explosive, they can form free radicals. like peroxides. They can produce unpleasant induction phase. So that time that it takes you to fall asleep during surgery, that can be quite unpleasant with the ethers. They are irritating and they can cause nausea and vomiting and even certain cancers. So it's definitely not a drug that they would like to use during general anesthetic procedures. But this drug has mainly been replaced by halothane, which is a halogenated hydrocarbon that we will look into just now. And it is no longer, the ethers are no longer used. But some of the structure-activity relationships that they could get from the ethers that assisted them in their lead development is that double bonds and halogens increases the anesthetic effect, while an increase in chain length increases the toxicity. So they found very similar type of SARs, especially with the chain length increase compared to the non-halogenated hydrocarbons. There's another halogenated hydrocarbon known as chloroform. Chloroform is also potent and produces good effects, but it has a narrow margin of safety and it does lead to liver and kidney toxicity, cardiac arrest, and arrhythmias. It can even lead to severe hypertension. So even though you do have this drug that can produce potent general anesthetic effects, it is not useful because of all of the adverse effects associated with it. But it was great that the researchers then found the ethers and chloroform, that it has anesthetic effects, because they used these ethers and chloroform again as a lead compound or as lead compounds then to further develop the agents into our halogenated hydrocarbons, like for instance, halothane that we will be discussing just now. So if we look at the halogenated hydrocarbons and why the halogen is important for this drug class, the halogens can reduce or eliminate the flammability and even reduce the explosiveness of these volatile general anesthetics. It can increase the potency due to an increase in lipophilicity. If you go on to maybe Swiss Atme and you draw these hydrocarbons, you can see that once you include a halogen into these hydrocarbons, that the log P value will always increase. So halogens do increase the lipophilicity. And it is also found that by the introduction of these halogens, that these hydrocarbons then get a reduction in toxicity as well. So you will see the halogens that were mainly used in the development of these halogenated hydrocarbons was bromine, chlorine, and fluorine. Bromine was found that it was not acceptable because it causes some toxicity. Chlorine-containing compounds only have limited use because they are toxic and can cause arrhythmias. But the addition of the fluorine halogen decreases flammability, the boiling point. It reduces the incidence of arrhythmias as well. So fluorine was found to be the best halogen to use in the development of these general anesthetic hydrocarbons. And something to take note of, if you look at the molecular mass of bromine, it's 80 grams per mole. Fluorine is 35 grams per mole. And fluorine is 19 grams per mole. So there's this increase in the size of the halogen. As there's an increase in the size of the halogen, so does the toxicity and other effects, it increases. So, or the adverse effects increases. So the smaller the halogen, like for instance the fluorine, the less toxicity you will have, better potency you will have less side effects, like for instance the arrhythmias and so. And they found that this is basically just related to the small size of the fluorine halogens. So you will see in the next slide, they talk about fluorinated hydrocarbons. So we've now moved from our hydrocarbons to our ethers, to our chloroform, and then to our halogenated hydrocarbons that contain chlorine, bromine, and fluorine. And now the researchers actually found, okay, we are on the right track. We found fluorinated hydrocarbons that shows good activity, good potency as a general anesthetic. It has good physical chemical properties, and there's not too many side effects associated with the fluorinated hydrocarbons. And here as well, you can see that they are the most useful general anesthetics, because the addition of the fluorine halogen decreases flammability, decreases the boiling point, decreases the incidence of arrhythmia, and it increases the potency of the general anesthetic. So you will see all of the drugs that are currently, or the majority of the hydrocarbons that are on the market currently, are the fluorinated hydrocarbons that are routinely used in a hospital setting where anesthesia is needed. So these fluorinated hydrocarbons is desflurane, enflurane, methoxyflurane, cefaflurane, isoflurane, and halothane. Please take a note, there's this fluorane. You will see there's quite a few of these drugs that have the name fluorane, and fluorane is always used for a general anesthetic. So whenever you see the name or the suffix fluorane, then you know you are working with a general anesthetic. You can see that these different halogenated or fluorinated hydrocarbons include halothane, enflurane, and all of the rest. What I would like you to do in this section is to draw up a table. I have the table here somewhere. It's a little bit later on in my slides. We can go back to that a little bit later on. But what I want you to do here is to go through each of these fluorinated hydrocarbons. I've already summarized the most important parts for you in my slides, as well as provided some additional information at the bottom of each of these slides. Make sure you go through this in your own time and also do additional reading in foyers, and maybe draw up a table where you compare and contrast between halothane, enflurane, sevoflurane, and the rest. And in that table where you have then a single snapshot of the different properties of each of these fluorinated hydrocarbons. An important section for me is where I've written down these notes underneath this fluorinated hydrocarbon slide of halothane. Please make sure to go through my notes carefully. I've tried to explain this to you in words to make it easier, and especially have a look at the maximum alveolar concentration. I've tried to simplify it here in the way that I understand it from reading through the textbook, to try and make it easier for you to understand what a maximum alveolar concentration is. Oh, sorry, excuse me, it's not maximum, it's minimum alveolar concentration. And this is the concentration of the drug in the lungs that is needed to prevent movement. So give the general anesthetic effect in 50% of subjects in response to the surgical stimulus. So it's important to know this definition, but also important to apply what you've learned here. So for instance, what happens when you have a low MAC? What happens when you have a high MAC? And all of that is now tried to explain here, and then also in your textbook chapter from page 517 to 520. Here you can also then have a look at enflurane, and you can see the MAC of enflurane is quite significantly higher than that of halothane. And you will then, if you go through my notes and if you read through the textbook, you will clearly see that what is the effect of this high minimum alveolar concentration. So I'm asking here the question, why is halothane less toxic? Is it because it's less potent? And does that then also lead to less toxicity? What do you think? So in my opinion, if something is highly, highly potent, you will probably see some toxic effects as well. And as you reduce the potency of a drug, you usually then also see a reduction in the toxic effects. Then you can just have a look and browse through the others as well, methoxyflurane and its general properties, as well as sevoflurane and its general properties. Make sure that you have a look at the minimum alveolar concentration and what it means. Make sure you understand it, because there may be a short question on the minimum alveolar concentration where I can ask you which of these drugs, based on their MAC, do you think will be the most potent? So here you can see that they actually do discuss it in the slides as well, when you can see that it has a rapid onset of action, and that is because of the minimum alveolar concentration and the high potency of this specific drug. So make sure that you have a look at the MAC, and if further information is required or further discussion is required regarding MAC, you can ask me during one of the face-to-face sessions to have a discussion on MAC as well. Then the fluorinated hydrocarbons, even though these drugs are the best that we currently have, they still do have some toxicities. Like, for instance, halothane is associated with hepatotoxicity. Some of these drugs can cause malignant hypothermia, where you get a massive increase in body temperature that can also lead to muscle rigidity, high fever, and a fast heart rate. And methoxyflurane, especially methoxyflurane, can cause some kidney toxicity as well. So that's why I said we still don't have the perfect or the ideal general anesthetic, because even the fluorinated hydrocarbons also have quite severe toxic effects if they are not used appropriately. So research continues to try and find even better general anesthetics. Then one general anesthetic that I would just like you to take note of, and you can do some background reading in 4 years, is nitric oxide. It is not a very potent general anesthetic. It also has the least toxic effects of all of the general anesthetics. It shows good anesthesia, but it has a slow onset of action. So it is not quick, so you'll have to inhale the gas maybe for 10, 15 minutes before you'll see the analgesic effects. And nitric oxide is just mainly used currently in dental procedures. Some dentists still use nitric oxide to cause an anesthetic effect during certain dental procedures. Then we also have our clinical useful intravenous general anesthetics. Now, this is basically just some pharmacological background. You do not have to know the structure, but know the different effects of propofol, ketamine, and etomidate. There's also some very nice background on the introduction video clip that tells you a little bit more about this intravenous general anesthetics and the effects that they have. Maybe it would also be good if you can draw all of this up in a table where you can compare and contrast between the different IV general anesthetic agents. We also get some general anesthetics, like, for instance, the barbiturates, like thiopental, which is an ultra short acting barbiturate that is also then used in anesthetic procedures, but it is usually used in combination with another general anesthetic to get the general anesthetic effect. Here is the table that I was referring to earlier. You can see here, if we do ask you to, maybe for the IV agents, write short notes or compare and contrast between the different physical chemical properties of the different IV agents, then you can see here what we expect from you, and also where you could then potentially get your marks from. We've also tried to guide you with some additional notes of what you need to look into if a question like this is asked in the exam. Then we also get our other general anesthetics, like our alcohols, because we did see that throughout history they have used ethanol as a general anesthetic. There are some structure-activity relationships that they were able to come up with the alcohols, even though the alcohols are non-specific drugs. These are the things that they picked up on, and it's mainly that the activity increases as the chain length increases. And please just make a correction here. It's not hypnotic activity, but it's the general anesthetic activity. Increases with an increase in chain length up to 8 carbons, and decreases if the chain length increases further. But also remember, even if you go from a 1 carbon to an 8 carbon, the 8 carbon will have more toxic effects compared to the 1 carbon. And that's probably because of the lipophilic nature. 8 carbon will be more lipophilic, more of the drug will reach the central nervous system. It will be highly potent, but it will also then be associated with more toxic effects compared to a 1 carbon alcohol. Whenever you see double or triple bonds, that increases the activity and the toxicity of the alcohols. Tertiary alcohols are more active than secondary versus primary alcohols. Chain branching, like we've seen in our drug design, increases activity. Halogenation increases activity, similar to what we've seen with the fluorinated hydrocarbons. If there's a second hydroxyl group in any of the chemical structures of the alcohols, it decreases toxicity as well as it decreases the activity of this drug class. So with this structure activity knowledge obtained, some alcohols have been synthesized to result in drugs that are more effective with less side effects compared to ethanol. But unfortunately, none of these drugs have made it onto the market. But this is just to show you that the research is still continuing And it seems as though that some of the researchers are thinking that different types of alcohols, and if we further do structural modification and structural improvement of the alcohols, we may even end up with drugs that are better than the fluorinated hydrocarbons. Please make sure that you go through my notes here at the bottom. I try to explain what is meant by saturated versus unsaturated chemical structures, and also what a primary, secondary, and a tertiary alcohol looks like. And as I said, the tertiary alcohols more active than secondary, more active than primary alcohols. Then here we have an example of some alcohols that have been developed by researchers that show some good anesthetic properties. But what I would like you to do on this slide is to arrange these compounds according to the highest and lowest general anesthetic potency. And I've given you a tip here, please use structure-activity relationships. So just to maybe quickly do that, if we then look at this structure here, this structure contains a tertiary alcohol. It has the double bond. It has a branched chain carbon, and it has 1, 2, 3, 4, 5 different carbons in a straight line. So this compound actually then has 1, 2, 3, 4 of the properties that makes it a good general anesthetic alcohol. So this one looks quite good. Compared to, let's say, for instance, the tribromoethanol. Tribromo, it contains the halogen, so that's 1, and it contains a primary alcohol. So if we compare tribromoethanol to methylpentanol, you will see that this one has 4 or maybe even 5 of the optimal properties for the alcohols to be general anesthetics, versus tribromoethanol only has 2. So obviously, when we compare these two with each other, the methylpentanol will have a higher potency compared to the tribromoethanol. But because it has all of these different optimal structure-activity relationships, this one will probably also be more potent, which will then possibly lead to more toxic effects as well. And you can do the same thing for the amyl alcohol and the chlorobutanol, where you can look at the different SARs and then rank them according to what you think is the highest to the lowest potency. Now, obviously, whenever I ask a question like this, I will always ask you to justify your answer as well. So some people may then, for instance, say that chlorobutanol is more potent than amyl alcohol and provide their reasons. And others will then say the amyl alcohol is more potent than the chlorobutanol, and they will provide their reasons. These two are quite close to one another. So based on your explanation, based on your justification, I will read through it. And if your justification is sound for your decision, you will still get your mark, because these two compounds are quite closely related. So it is your opinion, it is your justification, and it is your background knowledge that you will put down in your answer that will enable me then to see if you have made the proper, or that you've answered the question properly. So there will always be an opportunity for you to justify these type of answers as well. Then I think that brings us to the last slide. This is then just an exam question that I could ask, where I've asked you to describe the structure-activity relationships of the alcohols. And here you can see what you can include there. I will probably not ask this as an exam question. What I would rather ask is I will give you some of the alcohols and I'll ask you to rank them according to their potency, maybe even rank them according to their toxicity, but then accompany your answer with a valid justification of why you think that the one compound is more potent than the other. Okay, ladies and gentlemen, that brings me to the end of the general anesthetic lecture slides. I hope that you found this lecture interesting. And if there's anything that you would like further information on, you can post your questions on the discussion forums or bring your questions to the face-to-face session for discussion. I thank you.